Okay, everyone. Let's get settled in for the very last talk of the workshop. Yeah, we have Valentine, who is about to distinguish between chaos and order for us, an ongoing theme in Russell's research and the schedule for today. Thank you so much, Valentine.
So yeah, I was saying for people on Zoom that Russell deserves a myth, and that's what I'm providing with the help of some ancient sources from Greece and elsewhere. The Germans always helped with the terminology. So it's culture hero versus chaos monster, monster normally dragon. And the immortals, Blum, Mikali, and Yao, help the humans to understand what chaos really is. They say, you don't need that real thing. If it looks random to you, that's good enough. So yeah, we tame the chaos, go and use it. That's what they said. And then some people have started suspicions and doubts, really, is chaos completely tamed? Or maybe there's some kind of chaotic behavior left over, maybe. And indeed, as it turns out, there was some leftover of the chaos. You translate from random to random. There's still some hardness remaining. And actually, the two are kind of like the twins that were born out of chaos, and they're kind of equivalent to each other. And people started suspecting this, but they needed a hero to tell them the truth. Red flaming hair. People called him Russell. He showed the true nature of chaos. He said, you have this nice random generators in the crypto setting. You know what? They're actually equivalent to these hard things called one-way functions. So, you haven't gotten rid of chaos. It's still present in the form of one-way functions or hard things there. Another revelation. The first revelation was from the work of Russell with help of Levin and Ruby. Also came later on the white horse. Optimal complexity PRG is equivalent to this complexity PRG, so than crypto PRG. They turn out to be equivalent to another kind of hardness that exponential time requires circuits of exponential size. And that was an amazing result by Russell and other Dickerson in 1997. And slightly before that, Russell was really puzzled by how you can confine chaos in a somewhat hard function. And is it here or is it there? What does it mean to be a little bit chaotic or a little bit hard? And he had this idea, had that inside. If you have a little bit of chaos, then you can find a room where all of it can be put, and the rest is very nice and ordered. And that's hardcore lemma, which basically says that you can have a function which has a developed delta bound, and there's a room of size roughly 2 delta factors, where f is really bad. You don't go there, it's pretty random. But outside is all good. That was ancient history. Up to modern times. I was fortunate to be a student of Arvind at SSU in my master's program, and I kept hearing the stories that he would tell about his friend Russell, who would come to his office and tell him great things almost every morning. They would spend a lot of time together, and basically Russell was great at everything. He was a genius, and that's what I heard. And Arvind said, yeah, Steve Cook was also great, by the way. So, okay, I guess I was like thinking about those things and said, I should probably go to Toronto, yeah. So off I go to U of T. And I want to thank Arvind very much for being my advisor and for providing all the help. Setting me up on this arc that I'm going to tell you. '97 at U of T. Steve got copy of the proceedings of Stock 97. And as his custom, he would go through the papers and like put a bullet point next to the paper that looked interesting to him. And they will be like in the table of context, some papers would get like a special mark by Steve Cook. That was one of those papers that Steve marked as maybe important. And he said to me, this looks like a nice paper to read. We were reading stuff about like our functions or Rutherford's natural properties. You may be interested in this. And I said, yeah, sounds great. And then I tried reading it and tried reading it again. Come to Steve's office, telling I almost got it. Said, very good. Let's meet again next week. Next week I can. And after a few weeks, I kind of understood it. So it was, but back then people wrote paper in a very special laconic way. So it was very compact, just for the experts mostly. And yeah, I think it's like a lost art. Okay, 1998. Yeah, Toronto was a happening place in those days. Theory group was very active. And Theory group put up a complexity lower bounds workshop at the Fields Institute. Lots of great people came. Not our hero Russell yet, but Avi was there. And Avi talked about this recent paper that was not submitted to the conference even yet. That would become Fox 98 paper with Russell on randomness versus time randomization under uniform assumption. In his talk, Avi called it a gap theorem for de-randomization. I went to this talk and it was amazing, as usual. And the results, some of the results that they proved in this paper, the striking dichotomy between randomization and lower bound. They said either randomness is super powerful, like your randomized polytime algorithm is as powerful as exponential time machine, do exponentially difficult things, or you can expel some randomness and like get rid of randomness and randomize in sub-exponential time with some caveats that I don't want to go into, like average case version randomization. And there were some beautiful insights in the paper. Like I was working with Charlie Rakoff about this paper, and we were really excited and trying to understand all the details. A couple of insights from the paper were that breaking the instant distance to random generator would lead to a kind of learning algorithm for the function upon which the generator was based, approximate sense. That you would learn function f on almost all inputs, but not all. And you also need to use them. And then this kind of was more or less standard knowledge at the time, I think. But the new insight that nice, some nice properties, space function. And you can like do this extra and people understanding by and that's what allowed them to say, if you break my generator, my function was nice, and I will be able to without this function. My function was from X, and so I get that X was an infinity. Working with Charlie, talking to him a lot. We heard about Charlie earlier today. I like how excited to get sometimes. It was a lot of fun. And like we were really like studying this paper that I talked about, and I wrote my paper, which is similar ideas, and I was really here with my own. You said something similar to what it is, but not for PPT, or just error was error. Only the experts care about the difference. So the result says either because zero error randomized algorithm or you can randomize and I also got some. Oh, I really didn't realize it can be. All right. No, weird. Yeah, I also had an unconditional result that RP can be randomized, period. So you can place one-sided randomized algorithms in zero error, sub-exponential time algorithms infinitely often with some caveat that Leonor's comment is hiding, so it's perfect. The way I remember Avi telling Odette about this result, that basically he showed that RP is equal to ZPP. And I was sitting there thinking, yeah, maybe almost, yeah. But you know, Avi, he always likes to put things in the best possible way. Okay, so that was my first paper that I sent to this conference and got very nice reviews back. And then like 2000, Steve Cook turned 60 year before. And so it was high time to have a party for him. And the party was held at the Fields Institute, and this time Russell could come. So this time both Russell and Avi and lots of other great people were there. Beth was there, Edmonds, and lots of people. So that's first time I met Russell. That's my meeting Russell story. But I think I might have received some anonymous referee reports from him before. I think he was on this, I know he was on the CCC committee. He may have looked at my paper because I got some very nice reviews. Nice in a sense, I think you can prove this better thing too. And this is an idea of how you may approach that. And then he shows up and gives talks at the Fields, and I try to ask him like, yeah, like, what can we do? And he says, yeah, Avi and I have been thinking about some similar problems like in your paper, and here I have some ideas, and we started talking. So that was very exciting. And that led to this Easy Witness Lemma paper that appeared a year later. And I remember, yeah, we had like partial results, and I think I brought to, yeah, Complexity 2000 was in Italy, Florence, nice place. Russell was there. And I remember bringing a draft of this paper to Florence with me and showing it to Russell and giving him the paper copy, which I think he lost. So because it wasn't there next day, so he didn't get the, but fortunately nobody else used it because I don't think there were any author names there. I don't remember. So, but I remember like, I don't think we had this result back then, but I remember like getting back to Toronto and working, and eventually figured out how to get this, that if you have polynomial size circuits for any problem, for every problem in non-realistic exponential time, then you get a compression for your witnesses. So if you have a non-realistic verifier, non-realistic exponential time verifier, input X and some exponential long string Y. And if there exists any witness Y, which makes the verifier say 1, and you have this strong, unbelievably strong assumption, then you can show that you have a polynomial size circuit that encodes this Y viewed as a truth table of a Boolean function. So you have this easy witness from the assumption that your language is in polynomial size circuits. And I remember calling Russell from my office in Toronto and being very excited, telling him about this result. Like, Russell, I think we can improve this stuff that we had, and I think we can get this. And Russell, like, listening, and he doesn't need many sentences to get the idea. And he says, yeah, you're getting good results. Remember this, Russell? No. Yeah, so as a corollary of this, we also got that non-deterministic exponential time is equal to MA if and only if non-deterministic exponential time has small circuits. And the way we like to think about this is that, well, so first of all, NEXP is like non-deterministic exponential time. Merlin Arthur is like non-deterministic version of BPP. So like ignoring the n's everywhere, you say like either you don't have randomization because randomness is super powerful, or you have to have hardness. So like no randomization is possible unless you have circuit lower bounds for non-deterministic exponential time. So that was kind of interesting. And then different myth. Ryan took this easy witness lemma and applied it in a very interesting ways and improved it also. So in 2010, Ryan proved this beautiful circuit lower bound for NEXP not in constant depth AC0 circuits with mod 6 gates of polynomial size. And this easy witness lemma was used by him to get his hard function in non-deterministic exponential time rather than exponential time with an NP oracle. And then I guess he was not satisfied with this. And together with his student Cody Murray, they generalized the easy witness lemma. We talked about non-deterministic exponential time. These guys managed to talk about non-deterministic polynomial time and get some similar conclusions about the witness compression, which allowed them to improve this early result by Ryan from next mod in ACC0 to something like non-deterministic quasi-polynomial time in not an ACC0. As I would say, basically NP is not an ACC0. Okay. There you go. As logicians would say, it's morally NP, not an ACC0. Yes. 2001, I got a postdoc with Russell at UCSD. Tony mentioned today that she had been doing postdoc here as well. And one important piece of advice I got from Tony is to have breakfast with Russell every day. So like breakfast is the most important meal of the day, especially if you want to work with Russell. Back in those days, he would go for breakfast every day and we would go to this favorite place, which unfortunately doesn't exist anymore. So on the way to UCSD campus, we would stop at Elijah's, which Russell always called Samson's, I think, right? Yeah, because it was the name before, and then they changed the name, and eventually the restaurant was gone. It was a nice Jewish delicatessen place, but not here, not in that location. That location is completely kaput. Yeah, another nice German word. Like during those breakfast conversations, we talk math, and it's like early in the day, so everybody's really fresh. I'm a bit sleepy, but there's lots of unlimited amount of coffee in the place. And I think Russell had his usual Diet Coke in the morning. And then we would talk about things like, what can we work on? And I would say, well, what can we try to randomize? And Russell says, I don't know, maybe polynomial identity testing. Great, let's try. So what's polynomial identity testing? It's basically algebraic or arithmetic SAT. So in normal SAT, you have a Boolean circuit and you want to know some property of it, like if it's satisfying assignment, which makes them say true. In the arithmetic world, you have an arithmetic circuit with plus and times, say over infinite field. and you want to know if there is a non-zero or the circuit is identically zero on all possible assignments. And this is one of the few, some say the only natural problem in randomized polynomial time. It's in randomized polynomial time thanks to this ancient result due to Schwartz-Zippel and others, which say that with randomness, you just flip your random coins, pick the inputs up appropriately at random, and you'll know the answer with high probability. So the fact that it was kind of like sad actually helped us. But I'm getting ahead of myself. So before coming to UCSD, I was at IS and working with Avi, and like Avi told me at some point this beautiful result by Kaltofen, which allowed you to factor polynomials given by arithmetic circuits, and the factors will also be arithmetic circuits of small size. So you start with polynomial circuit of small size, arithmetic one, now relatively small degree, and you can like factorize it into its factors, polynomials, and they also be computable in polynomial size, which is kind of a miracle. And so I knew this at the back of my mind, and then I was trying to figure out how we can maybe use this hammer. And one of the first results we got was that adaptation of hardness randomness trade-offs from Boolean world to the arithmetic world. In the Boolean world, you know, like if you have a Boolean function of very high circuit complexity, Boolean circuit complexity, then you can build pseudorandom generators. And we did the same for the arithmetic world by taking permanent as our source of, or assumed source of arithmetic circuit complexity. So assuming permanent has like exponential arithmetic circuit complexity, we showed how to get a randomization for polynomial identity testing for circuits of like polynomial size and polynomial degree. So I was very happy with the result. We wrote it up, sent it to Fox. It got rejected. And I think, I don't remember, Russell, if you remember, but like maybe one of the reviewers said, it's nice. I just wish you could have like a converged direction maybe. And
making a strong assumption and only de-randomizing one particular problem. You know, why should PIT be hard to de-randomize some other method?
yeah, yeah. One thing I forgot to mention, Russell has a wonderful memory. He remembers like all his old papers and all the reviews. And he can also figure out who was the reviewer. So before we got this rejection, actually, we already had the second half of the paper, which I was thinking, we'll put it in the second paper after we got this one in. But then, okay, we had nothing better to do than put those two things together in the same paper. And so our second result, which we obtained while the Fox people were looking at our first paper, was that, yeah, actually, if you assume that polynomial identity testing can be randomized, then you do get some kind of circuit lower bounds. Well, maybe not exactly matching my assumption here, but you know, good enough. And with circuit lower bounds, you shouldn't be too picky because we don't have any. So you have either non-deterministic exponential time without NP poly or permanent requires like super polynomial size. And I think that made the reviewers of Stock conference happy. They accepted the paper, hooray. And yeah, the way we like to interpret this is randomization requires circuit lower bounds. When did I start? Okay, perfect. Oh, great. All right, so yeah, cut to the more modern times. 2015, fine-grained complexity at Simons, wonderful program. I think Ryan mentioned about this already in his talk. So it was my first Simons visits. I've been there a few times afterwards. I kind of like it there. So before that program, Antonina and I had this paper on compression of Boolean functions using the ideas from circuit lower bound proofs, kind of converting barriers into opportunities from the point of view of like lower bounds, which supposedly tell you something about the structure of easy circuits, easy functions, and extracting some algorithms from those and compressing Boolean functions. And eventually it became a paper with my student Ruben Chen, Ronen Shaltiel, and David Zuckerman in the audience there. And we used some beautiful work by Russell that was not mentioned yet. Oh, yeah, actually this one was. Paul mentioned this result by Russell, Matthews, and Paturi, like AC0 multi-switching stuff. And then there was another beautiful result that Russell did with Raghu Mecca and again David Zuckerman on pseudorandom generators for like De Morgan formulas, which achieve like non-trivial seed size or formula of up to cubic length, up to cubic size. And so what's the compression problem? It's a relaxation of learning problem where you're given a truth table of some Boolean function and you promised that this function does have a small circuit of polynomial size. Maybe even circuit is like very simple, AC0 or something like that. You're not given the circuit, but you promise it exists. And you ask to find any circuit which is better than the trivial one, better than 2n over n. And you can look at the truth table of the function, so you can run in time polynomial in 2 to the n, in time of the truth table. And so using some known results like AC0 lower bounds, we got the compression for AC0, but we didn't get anything for AC0 mod 2, or let alone anything higher than that. Okay. So that was like the prehistory of 2015 at Simons. And then Marco was there, who was really excited about natural proofs, as he still is. And he saw this paper on compression, and he got excited about that. And he says, can't we compress things better if we assume natural proofs rather than some special proofs that you were using in your paper? And Marco has been very persistent. By which I mean he would ask this question over and over again. Until one day, I think Russell was getting hungry. And he said, is it like D&D term, play to lose? No? Okay. Oh, you might be wrong. Yeah, I think it's used in some game playing. Let your character die kind of thing. Yeah. Really? Yeah. Or at least that's what Google tells me. So one afternoon, Russell said, let's play to lose. We'll use the NW generator. I've done something similar with Avi before in 1998. Remember I told you about this? Like we get learning from breaking the generator. So let's let the generator die and use that to compress the function upon which this generator was built. And I'm going to maybe mention a few more technical details in a moment, but this way, because we have, to break the generator, it was sufficient to use natural property to distinguish the outputs of the generator from truly random things. And we had natural properties for AC0 mod 2 from the beautiful work of Rasborough and Rudich. So using those ideas, yeah, actually that worked. It worked. Should have mentioned that Russell's idea worked. And we got the compression for AC0 mod 2. And then I remember Russell and I went to some talk in the CS department, and we were sitting next to each other, and he turns to me and says, don't we get like a learning algorithm as well for AC0 mod 2? And I thought about this for a minute and said, I think we do. And so that's how we got the learning algorithm for AC0 mod 2. And that became the CIKK paper that Antonina mentioned already in her talk. And so basic result is that if you have a natural property for a class of circuits, then you get learning under uniform distribution with membership queries. I think I'm going to skip the technical details. So, so you can think of natural property as kind of errorless, or as Marco said, algorithm with benign faults, errorless heuristic for minimum circuit size problem, which is a problem of given truth table, figure out if this is a truth table of an easy function or not. And Russell invited me to give a talk on Zoom in his lab meeting once to discuss CIKK. And I agreed. And while I was preparing for this talk, I was thinking like, what else can we do? Maybe we can use some Kolmogorov functions instead of natural property, which is like instead of MCSP, use some kind of Kolmogorov relative of MCSP, and maybe do something better. Because at the time, some people like Hirahara and Anashima had a result along this line saying that if I have some version of Kolmogorov complexities on average, then I can do some kind of learning. And their result was stated in a very strong form, like if distributional in P is an average P, then something good happens in learning. And like preparing for this presentation on CIKK, using natural property in mind, that, well, maybe the same thing works for KT or K capital T, which I don't really want to define it, but maybe I'll flash a slide in a moment. And it worked. So with my student, Haley Goldberg, we were able to adapt the Kolmogorov complexity natural property to get learning algorithms for class for which you have KT natural property under not just uniform, but p-sampleable distributions, and not just learning, but agnostically learning, and not from membership queries, but from random examples. So improvements happening there. And I guess I don't have time to define all the terms, but probably you can kind of guess what they mean. Unless there are any questions.
That's like pack learning, agnostic.
Yeah, it's kind of like restricted pack learning where the distribution is not arbitrary, but polynomial time, or polynomial size sampleable, actually. And maybe I'll show just this one kind of technical definition. So what's the difference between MCSP and K capital T? MCSP is an old problem that Leonid Levin talked about yesterday. You're given a long string, which you can think of as a truth table of a Boolean function. You're given a parameter S, and you want to know if there's a Boolean circuit of size at most S, which computes that Boolean function. And K capital T is the Kolmogorov relative of this notion, which Eric Allender introduced. He tried to make MCSP into like Kolmogorov kind of complexity measure, but keeping true to the form of MCSP, where you have like this local computation property. And the definition goes something like this. You're given X and the parameter, and you want to know if there is a pair description of a program and a time-bound T such that the program plus the time is small, and universal Turing machine given the description alpha of the program and any index I can tell you the ith bit of X within T steps. And you want to minimize this sum of size of alpha plus T. So you see you can compute locally every bit, but you have more relaxed access mechanism for K capital T, which allows you to do more things because it's a more powerful mechanism. And so intuitively, that's how you get better learning result from the stronger assumption. And without going through the technical slides, why is KT natural property better for learning? Well, the reason is kind of better is that we don't need to use Nissan-Wigderson generators. We can use much more naive generators than that, which don't require you to have like overlaps between different inputs to the generator. So you don't need to use any designs. And if you don't have designs, you don't have any interaction between your inputs, you can just fix them randomly, easily. And so you don't need membership queries anymore, roughly speaking. Okay, I know it was very fast, but that just gives you a flavor. And one very interesting question is whether you can do CIKK version for AC0 mod 2, but like show some kind of K capital T natural property for AC0 mod 2, which would allow you to learn AC0 mod 2 circuits from random examples, which in turn would allow you to break a bunch of conjectures of weak pseudo-random function generators that may be computable in AC0 mod 2, but conjectured. So this learning algorithm would kill those conjectures, but difficult. Yeah, Russ.
What does KT for AC0 mod 2 mean? Is it T going to be the size of the circuit? Or
That's a very good question. I think that's another open question.
yeah.
So before you can answer this question, you need to figure out what the definition is. But I think Marco has thought about this. So.
Yeah, I actually, okay, well, I don't know how much I thought about it, but I did write Eric Allender an email about it, and that's like thinking about it. And he says that actually coming up with the right definition of AC0 mod 2 KT is still open, and the difficulty involves AC0 mod 2 not being able to do a self-evaluation on a reasonable description of itself. So yeah, we can talk about that. That's a really exciting open problem.
Okay.
Marco is always excited about this thing, so great. Back to our hero. Struggling with chaos. There's been some progress. So hardcore lemma that Russell proved in '95 and rediscovered boosting algorithms by proving this lemma has found many applications that were already mentioned in previous talks, applications to dense model theorem in arithmetic progressions and primes, Green-Tao, Ziegler, explained in complexity theoretic language by these people, Rangel, Trevisan, Tulsiani, Vadan, applications to GAN algorithms, multi-calibration, regularity in graphs, and who knows what else. And Russell has been working on this problem for many, many years, at least 12. 15 maybe, yeah. So Russell has this nice Dropbox folder where he keeps the manuscript on this topic. And just before coming here, when I got an email from Russell that he updated the manuscript, and now it has like one first chapter on boosting, smooth boosting. So it's really exciting. And I'll show you this picture again. So I think this dragon is kind of weak. So Russell, you almost got him. You almost got him. So it's like, you need to continue.
Queen Khalifa, give me strength.
Yeah, exactly. Yeah, like you see, like this guy, one of the eyes is weird. You know, I don't know what you've done to it. So I'm sure there will be great results coming from Russell, as long as he can stay focused. And like he has some other adventures. So he's into singing and songwriting. And Ryan and Antonina better watch out, because just today in the morning, Russell was reading this on campus here. So you may lose him to the competition. Very close, actually. I think they knew.
It was on the path from Russell Lane to the coffee stand.
Somebody's tracking you, Russell. So I want to thank Russell for all the wonderful things he's done, and happy birthday, and looking forward to the next 60 years. And I want to show a couple more pictures. So this is the picture from a few years ago in my office with Russell. And if you zoom in, that's us 20 years ago when I was a postdoc at San Diego. I think it's in Russell's apartment. See how happy we were? Yeah. And that's typical Russell. And thank you very much, Russell.